So, in the last class we are doing retiming. We took the example of an IIR filter, something like this. Now, just simple first order IIR filter. Okay. So, if you see signal flow graph or data flow graph, it does not matter what you see, how you draw it here now. The signal source, it is generating x of n, then you are multiplying it by a factor maybe you can put a b here, b. So, b into x n, then you add b into x n plus, so this is a plus, and a into something. So, there is a multiplier with a into whatever comes, maybe y n minus 1 comes, that into a. When you add with this should be by this equation y n. So, if you assume that y n minus 1 is there already, it was calculated correctly in the previous cycle. So, just simply it gets multiplied by a and gets added here with b x n, then by this equation that will be y n. So, correct y n will be produced and it will continue cycle after cycle. In n plus 1 cycle, correct y n will be here multiplied by a, added with the correct new input and all those things. Okay. But we have done these kind of things earlier. So, there will be a delay, here is your y n. Okay. Now, what is the critical path? So, this is taking time t m, okay, multiplier, this is t a, this is t m. Now, t m plus t a, or if you take this side, you cannot go any further. So, if it is t m plus t a, so here I can do, just I can do a cut set retiming. This is one side of the one sector of the DFG, this is another sector, this is only one direction, no reverse direction. So, I can add any number of delay in this direction, I do not have to take out same number of delay from the opposite direction. So, you just put a delay here. So, now this multiplier and adder, they are not in the same cycle because the delay is separating them. So, T m, just if I had only this much, this node and this node, nothing else, then you have to take the larger of the two, T m or T a, you have to take T m. But now you have this side also. Here if you start at this, there is one output line, but this is delayed. So, this plus and this multiplication, they are not coming in the same cycle, they are separated by delay. But in the lower half, you have got T m, this multiplier, and then in the same cycle you are following up with the adder T a. So, T m plus T a. So, here I have T m, here I have T m plus T a, and here I have T m, here I have T a, here I have T m. Each node also is a edge. Each node is also a path actually. Okay, minimum, I mean shortest possible path. So, T m plus T a. So, I want to bring a delay here. So, if I do cut set retiming, this side is one sector. If you take out these two edges, this side is one sector, this side is on a single node, another sector. From left to right, I have got a delay. From right to left, no delay. So, you can take it out and you bring delay here. So, in this case, this multiplier and the adder, which were earlier in the same cycle, not separated by delay, they are now separated by delay. So, it will not be T m plus T a from this lower half, but for the upper half, it is becoming delay free. So, T a plus T m again. So, critical path will turn out to be T a plus T m. This is happening because as you know in retiming a loop, there is a loop here, total loop delay has to remain constant. So, earlier I had 1 d in the upper half, lower half no delay. So, total loop delay was 1. So, that has to be preserved. That is why now there is 1 delay in the lower half, but no delay in the upper half. So, the loop delay remains 1 same. Okay. All right. But can I bring down the critical path by some trick? The trick I can play here, you see, look at this equation, y n is equal to a times y n minus 1 plus b x n. Why n minus 1? I replace the left hand side by n minus 1. So, this becomes n minus 2, this becomes n minus 1. That means, y n minus 1 from the same equation can be written as a y n minus 2. When it is n, it is n minus 1. When it is n minus 1, it is n minus 2, a y n minus 2 plus b x n minus 1. This is this part from this equation. The left hand side, if it becomes y n minus 1, right hand side is this much, plus as before b x n. So, what you have is a square y n minus 2 plus a b x n minus 1 plus b x n. Now, if you draw the DFG or signal flow graph, you will see the loop delay will be increased to 2, not 1, 2, which will come to our advantage. Okay, how to have this equation? If you have this equation, now you see, I will erase this figure. And I will just draw the corresponding DFG for this. So, x n signal source b x n, then x n minus 1. A B they are all known beforehand. So, B or A B, these factors are known beforehand. There is a delay, they get added. Okay, A B, so B x n and A B x n minus 1 get added. So, I got this part. Now, with this I have a plus. So, this is the plus, this much with a plus. So, plus with what? Some a square times y n minus 2. So, suppose y n minus 2 is here. Suppose by some way I have got y n minus 2 here. So, simply I have to multiply by a constant a square and bring it back here. If you add, this will become your y n, and to complete the loop you bring in 2 delay here. Okay. Now, as before, I have a cut set retiming, the single path in one direction. Okay. This is one sector, this is another sector. I happily bring one delay here. Sorry. Okay. So, on this side, and here also I can do a cut set retiming. Okay. So, I can bring there, this is also forward direction. So, this is one side, the left hand side is another side. I have only one direction, 2 edges. So, I can happily add any delay here. So, I bring D here, D here. Okay. So, the upper half or lower half, if you go up to this, the multiplier and adder, they are not coming in the same cycle, separated by delay, here also separated by delay. So, T m and T a or T m and T a have to take larger of T m up to this, larger of T m and T a, which is T m. Then again I cannot go further, there is a delay, they are not coming in the same time. Now, comes here, here I have got T m plus T a, okay, T m plus T a. Here nothing, because after that there is a delay 2 d. Earlier I had 1 d, but because of this trick, it has become 2 d. So, if I now do cut set retiming, I just reduce 2 d to 1 d, that is take out one delay from this side, bring another delay on this side. Okay. So, now you see both this path is delayed, this path is delayed. So, adder and multiplier here or multiplier and adder, they are not coming in the same cycle. So, these are not delay free path, delay, which means on that node which takes maximum time, there is a multiplier that I have to take for the critical path. So, it is just T m, earlier it was T m plus T a. So, this is how I can bring down the critical path. But here I am paying a price, of course, that is on the input side. Earlier I had only one line x n into b, it was going directly here. Now, I have got two lines x n b, x n into x n minus 1 into a b. So, two multipliers, they are parallel, but I am paying more in hardware. This is the price I pay. I pay more in hardware and power, but I gain in speed because I could bring down the critical path. Okay. This kind of technique you can see in detail in Parhi's book, Parhi, as I told you, K. Parhi. Okay, they are called look ahead technique. That is, if you are standing at this index and looking ahead at a future index n, and you have got a delay between them, then the delay, the 2D, that could be used for doing the retiming. Okay. So, Parhi has actually developed one full, direction, one full way, topic of developing pipeline, designing pipeline IIR filters, okay, by various look ahead techniques. Okay, this is one. I pay in hardware, but I gain in speed. This is one good example. Okay. I will take another example, but then that is very involved, that is in the context of adaptive filter, and since I do not presume any background in adaptive filter, I will also develop, I will also tell you about adaptive filter equation, all those things. I will not derive anything here because it is not a course on adaptive filter, but then unless I really explain the background of adaptive filter, basic equations and all, then you will not be able to appreciate it. So, we will do that side by side. Okay. So far in digital filters, what you do? You design a filter to have particular pass band or stop band and all that. You design filter either by FIR method or by IIR method. Once you design them, they are fixed, the coefficients are fixed. Then you construct the filter, develop a circuit, okay, and it will remain as it is all along for all future. Okay, it will continue to do filtering of the input, produce the desired output. But suppose your purpose of filtering, the surrounding or all that, it changes, the requirement changes. Then you cannot throw away the filter and redesign another filter, put it in a circuit again. Can you, make the filter adjust itself to the new reality, new surroundings, okay, so that it remains the best filter, desired filter under the current situation. To give an example, suppose you have got one input sinusoid, okay, particular frequency, and it is added with lot of white noise, high power of high level of noise, okay, noise of high noise power. You have to filter out the noise as much as possible and pass that sinusoid. Okay. That is digital domain, maybe you have got a signal x n which has got some a cosine, some constant digital frequency plus some phase phi and some noise w n. W n is noise, is white noise with appreciable noise power. So, this signal is buried in noise. You have to recover the signal. What will you do? You will develop a band pass filter. You will design a band pass filter, narrow band around omega c and minus omega c, very narrow band. If the filter transfer function is this, it will be like this. So, the signal will pass through, most of the noise will not pass through because noise is white band, white noise. So, since the bands are very small, very narrow, most of the noise will remain outside the band, they will filter out. Very good, you design the filter once for all, be happy with this. As long as you get this kind of signals, it will be a beautiful band pass filter. But now, after some time, suppose the frequency of the input changes, omega c changes to a new frequency omega c prime. But you have not designed a band pass filter for omega c prime as the pass band frequency. Okay. So, your band pass filter which you designed and constructed, that will remove the signal also, because omega c prime is outside this band. But can I make it adaptive? Can I make it self adjusting, so that by looking at the input signal and doing some calculation, it can identify what it should do, what should be the desired response, and change the coefficients, change the filter coefficients, okay, maybe in an iterative manner, so that eventually you get, this filter becomes a new band pass filter, because you are changing the coefficients internally, the self adjustment process, filter coefficients are changing clock after clock after clock, in an iterative manner. So, eventually it should become another band pass filter, but its characteristics should be like this. So, now it will filter out noise outside the band, it will capture the signal omega c prime with frequency omega c prime. So, that means you need to adapt, the filter need to adapt itself. So, this adaptation mechanism, when you import to a filter, then this together is called adaptive filter. So, in adaptive filter coefficients are not held fixed, rather they are flexible by an internal algorithm of adaptation or adjustment. They are continuously adjusted from clock to clock to clock, so that depending on the circumstances or surroundings and all that, it always goes to the best filter. Okay, this is called adaptive filter. All right. I will show you the typical framework of an adaptive filter. What happens is this: x n is a random. I am taking them to be real valued, but they are all valid for complex case also. For our purpose is enough if we take real valued random signal. One is, what is given is E of x n, that is expected value at any index n, it is 0. Okay. And another is, if I define a vector, first let me come to this figure. X n is there, I am filtering it through a filter, FIR filter. Filter coefficients are like this: W0 to W n minus 1, capital N coefficients, 0, 1 up to n minus 1, output is y n. Output you can write as W0 times x n convolution sum, W1 times x n minus 1 plus dot 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 dot, last one is W n minus 1 x n minus n plus 1. Okay. Alternatively, you can write in a matrix vector form. Suppose I define a vector x n, starting coefficient x of n is x of n, next is x of n minus 1, next is x of n minus 2, dot 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 dot, last is x okay. This is your x n vector, and filter coefficient vector W, I put W0, then W1, then this entire y n can be written as W transpose x n in a very compact manner. Why W transpose? Because if you transpose W, it becomes a row vector, and then first guy W0 times x n, W1 times x n minus 1, dot dot dot. So, that is what it is. So, y n is W transpose x n. What is given? X of n is a real valued random signal. So, all samples are random, every sample has 0 random mean, and when it comes to correlation, there is expected value of this column vector into its transpose. This is transpose. So, column vector into a row vector. So, x n into x n, that is x square n, x n into x n minus 1, x n into x n minus 2, dot dot dot. That is called correlation, autocorrelation matrix, that is given to be R. See, they are function of n, but R is independent of n. That is because we assumed stationarity. There is input is stationary process. In fact, it is called wide state stationary. Let me tell you, though we are going little outside VLSI signal processing, but then this knowledge might be helpful. WSS. Typically, what is R? What is the I comma jth element here? I comma jth element will be x n minus I. Maybe you can take x n minus I from here, and then when you make a row, take x n minus j. So, x n minus I into x n minus j, that will come in the I comma jth position. So, R I j will be nothing but x n minus I, x n minus j. But though n is present, this is function of I and j only. This is the assumption of stationarity. That is, the two samples, I mean their correlation depends only on the gap between them. That is how close they are separated or how far they are separated. If they are far, correlation normally is less. If they are very close, correlation is high. So, gap between them will be, this index is n minus I, another is n minus j. So, if you subtract one from the other, say n minus j, if you subtract from n minus I, n cancels with n, that is why n disappears. So, it becomes a function of j minus I. So, it is basically a function of I and j two parameters, that is why R I j. Okay. So, under this assumption, R, which is the autocorrelation matrix, is independent of n. So, and mean also 0 for all samples. So, mean also does not depend on n, because of whatever be the index n, mean is 0. This is what is given. You have to process it through some filter coefficients, FIR filter. So, that output you can write in this way. How to design the coefficients? This is our task. This should be a very good estimate of some another signal d n, which is sometimes given to you, and during that time we call it training time, adaptation time, adjustment time. During that, using the given d n, you adapt it, the coefficients, to become a better filter, or whatever be the best filter required currently under the current circumstances. I mean adjust them, adapt them by some formula, clock by clock by clock, iteratively during that window. That time d n will be given, and then d n is not given afterwards. That time whatever filter you designed, you came with, be happy with that and use it for a while. Again a training period will come, and like that. So, d n is called the desired response, is also a random signal. This is also WSS, sorry. During training period, what I want to have the filter coefficients the best, that is y n should be a very good estimate of d n. That means, if I take the error between them, difference, this plus, this is minus, and this is the error, E n. So, E n, the power, E n is a random sequence also, because if x n is random, y n is random, d n is random, so E n is random. So, just square of E n, power is not enough, because I have to see statistically. Because it is a random thing, maybe at some index at a particular observation time, power may be less for that observation. Next time when you observe, power may be high. So, that is why instead of taking just E square n, we measure its average power, expected power, and this we minimize. Now, this is what d n minus y n. What is E n? And y n is this. Okay, y n is this. So, if you substitute y n as this, d n minus w 0 x n minus w 1 x n minus 1 dot 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 and square up, and then apply E expected value, this entire thing will be a function of what? W0 square, W1 square, W2 square, W1 square and W0 W1, W1 W2, W0 W2. So, it will be a second order function of all the coefficients. I have to minimize the second order coefficient with respect to this coefficient. So, that for whatever coefficient, I mean this is the minima, that is the best. So, I have to take partial derivative of this entire thing with respect to W0 equate to 0, with respect to W1 equate to 0, with respect to W2 equate to 0. And second order when derived will become first order. So, we will get, as we see, we will get a set of equations, first order equation, which will give a unique solution. That solution will give rise to the best W0, W1, all that. That will be called the optimum filter. Before that, there is one more thing on Dn. Dn also is assumed to be jointly stationary with Xn. Means, if you take correlation between Dn and any sample of Xn, that will not depend on n, that will only depend on gap between Dn, that is n, index n and the index, whatever is the index you have. Okay. So, it will therefore, another vector that we consider here is P, which is the E of this Xn Dn. Okay, Xn Dn. There is Dn, if you multiply this Xn vector, see all vectors are denoted with underscore. Yeah, I should have mentioned this. All numbers, all variables which are underscore, that indicates a vector. When if it is a lowercase with underscore, it is a vector, column vector. If you take a row vector, that means the transpose of a column vector. So, we follow a notation, every column vector is denoted by a lowercase letter with a underscore. Row vector means first draw the column vector, then put a transpose on it, so that it becomes row. For a matrix, again we use the uppercase letter, but with the underscore. So, we use the underscore. If it is lowercase, it is a vector only. If it is the uppercase letter, it is a matrix only. But if there is no underscore, it does not matter whether it is lowercase or uppercase, it will be a scalar. So, P is E Xn underscore. So, this is the Xn vector into Dn. Dn is a scalar, no underscore. So, Xn vector into Dn means this into Dn, this into Dn, this into Dn, this into Dn, all the samples of Xn into Dn. So, another vector and E on them. As I told you, if it is jointly stationary, say Xn into Dn, that will not depend on n, index n here, so gap is 0. So, it will be just a function, I mean it will be just some constant. Then if it is Dn and Xn minus 1, okay, then gap is 1, and then if it is Dn and Xn minus 2, gap is 2, so on and so forth. Okay, that is why it is independent of n, and that is what is given to you. Okay, so we will start, we will cover this in the next half. Thank you.